Do you know what are the various shapes and forms of abstraction are floating around us? When you are writing a Verilog code, do you know what level of abstraction you are following? Can you map various style of Verilog coding to its respective level of abstraction? Do you know what are the various levels of abstraction exist in VLSI design? Among all these levels of abstraction, do you know what levels are synthesizable by USIS? Stay tuned till the end of the video to know all the answers. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will discuss the various kinds of abstraction that we see in our day-to-day life. That is, the abstractions that is around us, so that we can correlate the generally seen abstraction with the abstraction of the VLSI design. This will simplify the concept of abstraction so that you can easily grasp different level of abstraction that is found in the VLSI design, starting with the synthesis. Next, we will talk about benefits of abstraction levels in VLSI. As I have mentioned that first we simplify the abstraction concept and then we will elaborate the abstraction levels in VLSI, and this way you will easily plunge into the abstraction concept in VLSI. Next, we will talk about levels of abstraction and synthesis. Next, we will go in detail about the system level abstraction. We will go for the definition and elaboration. Next, we will talk about high-level abstraction. Obviously, all these abstraction inside VLSI and not outside VLSI. Next, we will talk about behavioral level abstraction. Next, we will talk about register transfer level, that is RTL abstraction in VLSI. Next, we will talk about logic gate level abstraction, and then we finally summarize our entire discussion of this episode. So that's the menu for today. Without any further delay, let's begin. Various abstractions around us. Now in this particular slide, we are going to talk about the various shape and form of abstraction that we can see in various sectors of our life. Now let us start describing them. In programming, as you learn the computer as an engineer, the programming is the first thing. Probably C is the first programming language that nowadays you learn when you learn the computer application. What is the abstraction in the programming? In computer programming, abstraction involves creating functions, classes, and objects that encapsulate complex operation. I think few weeks back, we have just covered the object-oriented concept in the Python. And there I have talked about these various things, that is classes, object, encapsulation. And in case you have seen that episode, you will be easily relating that. And in case you are a student who have learned the C++ or Java already, they can also correlate these concepts. This allows developers to interact with the high-level, easy-to-understand interfaces while underlying complex code remains hidden. This is a way of handling the computer code. That means the code which we are writing for our purpose, either through C++ or through Java or Python object-oriented language or Perl object-oriented language, anything. There we make our complex world simple in terms of object-oriented tools and elements. In our channel, we have both the Perl object-oriented concept and example, as well as Python object-oriented programming concept and example we have already explained. You can watch those two episodes from the two different playlists of Perl and Python in case you want to have a glimpse of what we are saying here. Now, we will come out of the context of the programming, and the next thing that we see around us is art. Art is basically something that is what we do with painting brush, right? So here what is the abstraction? In art, abstraction involves representing objects or scenes in a simplified or stylized manner. This can evoke emotions and ideas without presenting a detailed and realistic depiction. You can see different artists who depict modern day art in their, maybe they are running a show in some art gallery. There you will see the modern arts, they are constructed of abstract shapes and ideas, where maybe the painting is depicting only one thought or maybe some more thought, not more than that. So that means a picture can have multiple details like what you have in a Mona Lisa painting versus today's modern art, where the abstract art is much more simplistic way of expressing some particular emotion, or the artist want to send some message. So this is the abstraction which make complex thing simple. So both programming and art, what is the abstraction does? It does the simplification of a very complex thing in some sort of representation. Next, in science, in scientific model, abstraction is used to represent complex phenomena with simplified equation and diagrams. This model helps scientists understand the underlying principles without getting lost in intricate details. This is a concept which you might get familiar in case you are very much connected with different scientific societies, or in case you are maybe reading scientific articles. Here, in the first paragraph of any scientific article, you will see that there is a small paragraph which is called abstract, and there things are written in a very telegraphic manner of words just to depict what the complex paper means. So looking at that abstract, you will be able to correlate the gist of the whole paper. And sometimes when author is sending such papers to some conference or journal, first he or she need to send only the abstract so that there is a green signal from the authority to send the entire paper. Like that, the abstract means you make a simplified form of the whole paper in a much more simple version, which is called the abstract. So when you are sending a paper to a conference, generally first you will send the abstract. Once it is accepted, then you will send the full version of the paper. So this is also seen in the science. So the abstract means simplification of any detailed and complex thing. So here you can see in programming, art and science, this is a very same underlying concept that exists for abstraction. Next, we have engineering. In engineering, the abstraction helps break down complex systems into manageable components. For example, a car's engine can be abstracted as a black box with inputs and outputs, ignoring the internal mechanisms. Generally, in such cases of hardcore engineering, I am not talking about the soft engineering that we do with the code or something, that already we have talked already here in this programming. Now, which is a hardcore engineering, like a mechanical engineering, like a civil engineering. There, you will be doing a lot of diagrams, and maybe you have to make some simple structures also with maybe wood or maybe paper or something like that to make a simplified version of the project that you are going to complete. So this is the abstraction. That means abstraction means you are making a short and sweet version of the entire complex thing, complex project that you are going to execute. So far we have covered the 1, 2, 3, 4 points. That is 4 points about programming, art, science and engineering. What does abstraction means? Next, in VLSI. Now let us focus on the VLSI. In VLSI, that is very large scale integration, abstraction refers to the process of simplifying the representation of a digital circuit or systems while retaining its essential functionality. This is a crucial in VLSI design where the complexity of the modern integrated circuit can be overwhelming. Abstraction enables engineers to make complexity by focusing higher level of views of the design which are easier to work with and understand. For a chip, if you want to express it, in last episode we have talked about the V curve, where you descend one by one and then ascend one by one to make the entire chip. In case you have not seen that episode, please watch that episode, the first episode of the synthesis. And again, now if we make a common line about the abstraction, it means that we represent any complex systems in either programming or art or science or engineering, and in VLSI we make a simplified model or simplified format or simplified shape or maybe diagram of the very complex thing which will require maybe a team of 50 people to achieve in a very short and sweet manner, so that is very much easily understandable. Maybe the person in the company who is allocating the budget for that, so for that person to understand that thing, because he will be from the finance and all, right, and that person will be allocating budget, so that person has to understand in a very simplified manner that what the engineering team is going to do. So So the simplified format, not the detailed format, not the hardware language code and all, but maybe in a simple diagram or maybe simple block diagram, that will help the design team to obtain the necessary finance for that particular project, and also will receive a green signal for that. So this is the abstraction that exists in any of programming, art, science, engineering or VLSI, which we are talking about. Now here in this particular slide, we have generalized the concept of abstraction in all the sort of complex thing that we see around us, and it is for multiple areas of operation. So we are done here. So let's move on to the next slide. Benefits of abstraction levels in VLSI. Now we will go thorough detail of the benefits that we have of the abstraction in VLSI. Each abstraction levels allows engineers to work at suitable granularity depending on the design stage and goals. So they may be front end, we are starting there, the abstraction level will be something. Once we go to maybe NTFT, the abstraction level will be different. Once we go to the PD, the abstraction level will be different. This way, we will have necessary abstraction level at different point of the entire VLSI design flow. And here I am talking about the ASIC. And in case of analog design, obviously there will also be relevant abstraction levels. During the design process, engineers often start with the higher level of abstraction to capture the functionality of the overall structure. And I was talking about that the design team, say 50 people spread across the entire global different locations, they have to get their financial sanction for that particular project. So they have to submit an abstract of the entire chip that they are going to design. In that case, they will have to start from the highest level of the abstraction. Next, as the design progresses, they refine the abstraction, eventually reaching the transistor level representation for detailed analysis before fabrication. As I have said, as we go down, say from front end to a DFT, then we enter the back end and all the necessary steps for the PNR and then the routing, and then next going for the physical verification, going for the different levels that we go through, as we have talked about the different steps in a VLSI design in last episode. Please go ahead and watch that particular episode in case you want to know what are the different steps in a VLSI design. So as we proceed through those steps, the abstraction representation that is changing at every different stages, maybe after certain levels, where the design mode or the concept is very different from the first zone to the second zone. So the zone will be the proper word. In the entire VLSI design, we move from one zone to another zone, and each zone the abstraction level will be different. Abstraction in VLSI design helps to manage the intricate details in manufacturing process, optimize performance, and ensure correctness. Ultimately, the VLSI design is a concept to reality process, and that concept starts with a conceptual abstraction, then it goes in detail for the design purpose, and each zone the abstraction representation gets changed, and going deeper in the VLSI flow or going further in a VLSI flow, the abstraction will contain much more details as compared to its previous step, because from the top level we are approaching up to the transistor. It allows engineers to approach the design from different angles. I said different zones are there in the VLSI design. Each zone, different engineers will see it from different angle. Some will see as a AGL code, some will see it as a layout, some will see it as a test, right? Testing either its functionality or the fault testing. And someone they will see is as a physical verification. That means the challenges that will have to be dealt in the real fabrication process. Enabling efficient collaboration and easing the transition between different stages of the VLSI design process. Now, different stages of the VLSI design process, which I was mentioning as different zones of the VLSI design. So these are the different benefits of the abstraction levels that we have. Now we are done in this particular slide. Let's move on to the next slide. Now here we will talk about different level of abstraction. This is basically a flow chart with different levels of abstraction that are there in VLSI design, and we will encapsulate the part which is for synthesis and specifically which is done by the USIS, which we are learning in this particular series. First, there is the system level abstraction, which is the top level and the most simple form of abstraction. Next is the high level abstraction. As we go further down, we have behavioral level of abstraction. Next, we have RTL, that is register transfer level abstraction. Don't worry, we will go in detail one by one of these levels in upcoming slides. Next, we will go for the logic gate level abstraction. As we go further down, we will encounter the physical gate level abstraction. And then we will go further down. We will find the switch level, that is the CMOS switch level abstraction. Now, this was the flowchart of different system levels as we go deeper, right? Now, let us see some more additional details which will help us to understand. This system design interconnects these two level of abstraction. High level synthesis will interconnect these two. So these two, the behavioral level synthesis will interconnect these two levels. Next, we have RTL synthesis. This particular synthesis will interconnect within these two levels of abstraction. Next is the logic synthesis. This will interconnect these two levels of abstraction. Next, we have a cell level library, which we will achieve by interconnecting these two levels of abstraction. Let me recap. System level design. The system design will happen once we make a transition from here to here. High level synthesis will happen once we make transition from here to here. Behavioral synthesis, that is this one, will happen once we move from behavioral level abstraction to the register level abstraction. RTL synthesis will happen from this to this. Logic synthesis will happen from this to this transition. And cell library will happen from this to this transition. Now our question is, what does the EOSIS cover? So the EOSIS will cover these three particular levels. That means from this level up to this level: behavioral level, RTL level, logic level, and physical gate. So these four levels of abstraction will be covered by EOSIS through behavioral synthesis, RTL synthesis, logic synthesis. Don't worry, we have detailed explanations coming up in next couple of slides. So we are done with this particular slide. Let's move on to the next slide. System level abstraction. System level abstraction focuses on major components like CPUs and cores. So this is the top level one. High level description uses languages like C, C++ or MATLAB. So this is designed in very high level language, maybe in MATLAB. Special software libraries like System C aid in simulating circuit at this particular level. So you can see there are different languages to represent this system level abstraction. System level usually avoid automated synthesis for lower level representation. System level design tools facilitate interconnecting building blocks. The IEEE standard 1685-2009 standard establishes IP exact file format. So this is something you can go and search in the internet. This format represents the system level designs and building blocks for such particular designs. Here you have a glimpse of the system level abstraction. You can see here System C, MATLAB, Simulink, all these kind of things, and IP exact. These things are used for system level abstraction process. We are done here with this particular slide. So let's move on to the next slide. High level abstraction. High-level abstraction, algorithm level, employs traditional programming languages. High-level abstraction, that is the algorithmic level, employs traditional programming language. These languages have limited features, like with C language, restricted pointer usage to mimic hardware concept. We are talking about high-level abstraction. In the high-level C representation, pointers simulate hardware ideas like memory interfaces. However, advanced dynamic memory management is not allowed as it lacks digital circuit equivalent. So there is a limitation, and hence the level of abstraction is much more simple, how one particular block interacts with another, and it is written in the high level programming language, that is C. Synthesis tools convert high level code like C, C++, System C with metadata into behavioral level HDL code. This is also possible. Commercial and FOSS tools for high-level synthesis are available. FOSS is nothing but the free and open source software like EOSIS. These tools transform high-level code into Verilog or VHDL code for implementation. Now you understand that you are writing in different language, and this particular synthesis tool will transfer it to another level, as we have seen in the previous slide where we had the flowchart, right? And this is about the high-level abstraction. In simple words, we define it by the high-level programming language, then we use either commercial or free and open source tools to convert those high-level abstraction, that means high-level codes, into Verilog or VHDL representation. So that's all we have to say in this particular slide. Let's move on to the next slide. Behavioral level abstraction. Here we will have the bullets to define different subtopics. First, we start with behavioral abstraction. It utilizes the hardware description language like Verilog or VHDL and incorporates behavioral modeling in circuit representation. Next is the behavioral modeling. It employs the imperative programming for data paths and registers. It utilizes construct like always block in Verilog and process block in VHDL. For detailed understanding of the behavioral modeling, we already have an episode on Verilog. Here is the thumbnail. You can find it from the Verilog playlist and you can go in detail of the behavioral modeling, from where you will understand the behavioral abstraction also and about these always blocks, etc. Right here you can see initial and always is written here. So you will use this particular shown episode to understand in detail of the behavioral modeling, and at this level we use the behavioral abstraction through the languages Verilog. So we have our series on Verilog, so we can easily understand by watching this particular episode. Next, code fragments and sensitivity. Behavioral modeling include code segments with sensitivity list like signal and conditions. These are also there. In simulation, execution upon sensitivity list changes or conditions triggered. So all these things are there in this particular episode. If you watch this, you will understand what we are meaning in terms of Verilog. Synthesis transformation. Synthesis converts this representation into suitable data paths and registers. Ensures alignment with the hardware description. So here we have talked about the behavioral level abstraction, which we also have a detailed episode to the Verilog, and all the points here you can correlate if you go through this particular episode. And for synthesis part, we will come up once we have our actual hands-on practical later in this particular synthesis series. So we are done in this particular slide. Let's move on to the next slide. Register transfer level, that is RTL abstraction, and here we have written a short form of abstraction as ABS as there were no spaces. Now first point is that RTL, that is the register transfer level design, involves combinational data paths and registers, usually D flip-flops. This is a kind of different style of doing the coding in Verilog, or the abstraction will be also different. Verilog code at RTL represent designs using combinational logic and registers. So this Verilog coding is all different from the behavioral modeling which we have talked in last slide, and we have shown a thumbnail. Example, assign PMP equal to A plus B. So combinational data path, always at the rate posage of clock, register Y. We have this assignment operator that is less than equal to, and then it is one of the examples, right? This is about the combinational logic. RTL representation uses HDLs like Verilog and VHDL with minimalistic always blocks or process blocks. So it is in comparison with the behavioral modeling. Here we have very less number of always blocks or process block in VHDL. Always block is in Verilog and process in VHDL. HDL simplify RTL simulation, no added tools are required. This is another point. Simulation tool is enough to do the things here. RTL allows optimizations like FSM detection, memory identification, and resource sharing. So you will understand all these things because we have different sub-binaries inside EOSys to do this kind of optimizations like FSM detection, memory identification, etc. RTL represents circuits as graphs of registers, combinational cells, and signals. Graph means there will be a pictorial representation where we have different branches. Encoded graph is called a netlist. So once we encode this particular graph, we derive a netlist. RTL synthesis replaces netlist elements with the gate level circuit. It's a very simple transformation, and hence it will not go in a vivid level. It will just transfer the basic, say here you are using the combinational circuit and registers, right? Those will be converted, taken from the standard cell library, that is the PDK or DK. Whatever you have from there, it will pick up those and place those in your code. It is a very simple synthesis, and it is the RTL level synthesis. RTL synthesis includes sophisticated optimization within RTL representation. So it is very much sophisticated, and here the design from very beginning, the representation will be in terms of blocks. One block is connected to another block, one block is sending signals to another block, and they are sending it further or maybe concluding as an output. So this is a very simple thing. Few FOSS tools for specific RTL synthesis tasks, but none covering a wide range. This is one limitation you have. And in case you want to learn about this particular RTL type of abstraction, please see this type of modeling, the data flow modeling, which we have talked about in Verilog. So there you will be able to correlate what we have talked here with some of the example of codes. So you can find this particular episode from our Verilog playlist available in our channel. So we are done talking about the RTL level abstraction and the RTL coding in Verilog, which we already have one episode. Thumbnail is already in front of you. You can go watch it. Why I am giving these episode examples in Verilog? So that you can actually map the abstraction with the set of respective codes. We're done here. Let's move on to the next slide. Logic gate level abstraction. So here we have first point. Logic gate level represents designs using netlist comprising basic logic gates, that is AND, OR, NOT, XOR and register, three-type flip-flops. Netlist formats include ARIF, while using netlist like VHDL or Verilog are commonly used for simulation ease. Logic synthesis involves optimizing gate level netlist and mapping them physically available gate types. Two challenges: optimization within gate level netlist and optimal mapping to the physical gate. So these are the two challenges in this particular level of abstraction and synthesis. Since we are talking about the synthesis and its respective abstraction in the same slide, so we are talking about the abstraction, what it means, and we are going into the maybe code, and we are talking about the synthesis. So all are tightly packed in one particular slide. So even this is true for the previous couple of slides where we have talked about different other level of abstraction. Two-level logic synthesis is basic, converting logic function into sum of products using method like Carnot maps. Modern tools uses a multi-level logic synthesis based on binary decision diagram (BDD) and inverter graphs, that is AIG. These are internal algorithms of the tools that we have today for synthesis. BDD ensures the normalized form. AIG offers the better post-case performance for large logic functions. Now, why we have this algorithm? Because ultimately the synthesis tool, if someone has written it right in terms of code, and that code has to perform the kind of synthesis at different levels. So at different levels, they have designed different processes, or you can say optimizations, etc. So those are here. You can see the names, and here you have to just get familiar with them. And once you go into the detail in the manual, you will get involved in this particular kind of applications and application oriented methods. FOSS tools exist for multi-level logic synthesis. EOSys provide basic logic synthesis, can use ABC for logic synthesis. So EOSys has another binary in its installation called EOSys-ABC that can be used for this kind of logic synthesis. I was saying that software writers, that means the programmers, have to write different set of algorithms for different level of abstraction and for the different type of synthesis. And we have a detailed episode on the gate level modeling, which you can correlate. As we have said, we are using logic gates and registers. This kind of modeling we already shown in this Verilog episode. Go ahead and find this particular episode from the Verilog playlist in our channel, so that you will be readily grasp the meaning of logic level abstraction. That means how a design is expressed in terms of logic. So you can see even short form of the diagrams are there also. But for detail, you go ahead and see this particular level. This is abstraction, what we do in the Verilog code. And once we synthesize it, we are using internal algorithms of the synthesis tool to take it to the next level. We're done here. Let's move on to the next slide. Summary. So we have talked a lot of different types of abstraction that exist, and we have also guided you to see the different level of Verilog episodes to correlate them, and the synthesis algorithms you will come across once we go in detail of the EOSys. So there you will go in detail and you will see how these things matter. But the learning has to be in a sequential format for different episodes. So we are making you familiar with different level of abstraction and the corresponding Verilog code and the different synthesis algorithm that exist. So let us summarize what we have talked about in this particular episode. Behavioral level abstraction. This is the highest level of abstraction. It focuses on the functional behavior of the circuit without entering into the implementation details. Engineers describe this, the desired functionality, using high level languages like Verilog or VHDL. So this is a behavioral abstraction. Next, we have RTL level of abstraction. At this level, the design is represented in terms of register, logic operation, data transfers. It provides a more detailed view of the circuit operation but still abstracts away from the lower level implementation specifications. Next, we have gate level abstraction. Here the design is represented in terms of basic logic gates, that is AND or NOT, etc. The abstraction captures the logic relationships but ignores the physical properties of the components. That means we do not have the details from the standard cell library, the PDK or the TK, in any of this level of abstraction. Once we do the synthesis, the technology data comes from the standard cell library, PDK or the DK, and get attached with the synthesis tool as we have shown in the flowchart in the last episode, and goes to the next step of each of these abstraction through synthesis. Transistor level or layout abstraction. This level involves modeling of the circuit using individual transistors. So this is not really at Verilog or VHDL level. This is at layout level. Maybe a full custom layout engineer will be doing these things, or maybe a semi-custom engineer also, or maybe a IP design engineer is doing that. So it's the closest abstraction to the physical implementation. That means you are designing it at the layout level, where you have tracks and different standard cells or different versions, all those things, providing insights into the electrical behavior of the design. That is why we have the standard cell characterization. That means where we characterize the electrical properties of all the standard cell that we design by hand in layout as well as maybe in the code. So we have learned all of this, the different prominent level of abstraction that is existing in the VLSI design, and eventually without knowing the type of abstraction you will enter into this as you go through the Verilog code or maybe VHDL code, or maybe you are a standard cell designer. So in that case you do not know that you are using this particular abstraction and you are going to the next level of synthesis using a particular VLSI tool. So we have talked about the different level of abstraction specifically, and also in this episode we have shown you the 3 different types of synthesis that is taken care by the EOSys, the free and open source tool. So that's all we have to say for this slide. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.